A 4-bit model can be perfect for CPU and painful on GPU. Benchmark GGUF, GPTQ, and AWQ against your hardware before choosing the runtime. After this, you'll understand how to assemble a pipeline that compares model packages by memory and speed and picks the best fit. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. When you move a model from research to production, the choices multiply quickly. Quantization saves memory. Yes, but formats and runtimes behave very differently in the wild. Engineers pick GGUF, GPTQ, or AWQ because they let larger models run on cheaper hardware. The real question is practical. Which format actually fits your host? And which runtime gives users a responsive experience? We measure TTFT, time to first token, and tokens per second to capture those two sides. GGUF, GPTQ, and AWQ are basically packaging and quantization choices tied to different runtimes. GGUF often pairs with lightweight C runtimes like llama.cpp. GPTQ files usually land in transformers-based Python stacks. AWQ targets newer high-performance backends like vLLM. The job is to match format and runtime to RAM and VRAM limits, while keeping TTFT low and throughput acceptable. Fit matters more than raw claims on paper. We will build a small comparator that checks memory viability, verifies the runtime endpoints, runs a compact streaming latency check, and decides which artifact to promote. That pipeline mirrors real incidents where a model file fits memory but fails in the actual service path. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we list artifacts and estimated memory to filter impossible choices. That keeps the experiment realistic and avoids wasting benchmarking cycles. This snippet gives you a quick hardware fit filter, so you only benchmark artifacts that can actually load. It declares an artifacts table with GGUF, AWQ, and GPTQ entries alongside small RAM and VRAM estimates, and then marks which ones fit the host budget. The names hint at common pairings. GGUF, llama.cpp, AWQ, vLLM, GPTQ, transformers, and the numbers are planning estimates you should replace with measurements from your target model and machine. Next, we must confirm the runtimes are reachable, so our benchmark hits the right servers. Reachability saves time and prevents false failures. This example confirms the inference endpoints are actually answering before we spend time benchmarking. It builds a client's dictionary, pointing at each runtime, and calls models.list as a cheap readiness probe. That ready-s check is not a cold load benchmark. It simply verifies the runtimes we expect are visible and exposing models, which prevents routing mistakes like hitting the wrong port or an unexpected model. With memory viability and endpoints confirmed, we need a compact, apples-to-apples latency primitive that works across backends. That keeps the comparison fair. This code provides a small, consistent benchmark function used against every backend. It calls the same OpenAI-compatible client.chat.completions.create and treats the first stream chunk as TTFT, then measures total elapsed time to compute tokens per second from max tokens. Keeping the call shape identical avoids comparing different measurement styles, and the helper returns comparable TTFT and throughput numbers you can use in the next step. Now we run the actual comparison by calling the same prompt against each live endpoint and collecting TTFT and throughput. This is where surprises usually appear. This snippet runs the apples-to-apples comparison across live endpoints and collects the key metrics. It sends the same prompt through client's GGUF and client's AWQ via stream metric, then stores TTFT, token/s, and response size in a stats dictionary. That way, you see both latency and throughput together. A high tokens per second number doesn't save you if TTFT is terrible or the artifact fails quality checks. And the output immediately names which live path looked faster for this run. Finally, we convert those numbers into a simple release decision that respects both fit and performance targets. That makes the choice repeatable for teams. This example turns the benchmark results into a concrete promotion rule, so teams can act without guesswork. It applies a limits dictionary for TTFT and minimum token/s, intersects passing formats with the earlier viable memory filter, and picks a winner. If nothing meets the bar, pool falls back to formats that at least fit memory and were benchmarked, which helps debugging instead of failing silently. The printed output shows the chosen baseline and how many formats cleared the thresholds. In a real deployment, you'd run this on a canary machine, validate TTFT and throughput against typical props, and check quality before rolling the chosen artifact to a cluster. The comparator gives you a practical gate. It's not the whole QA story, but it tells you when a format deserves a canary. Use this approach when you need a practical yes or no about a model format on real hardware, or when multiple runtimes claim compatibility and you need measurable signals. One caveat: synthetic benchmarks are useful, but nothing replaces a short canary against real user prompts and cold start conditions. As a next step, tweak the limits in the decision step and run the pipeline against your target model and host. In practice, raise the minimum tokens per second requirement and tighten the TTFT cap. Then see which formats survive those production constraints. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.